Welcome to Learning Chemistry with Faye. In this video, we will learn how to determine chemical formulas using chemical compositions, and we will also learn how to convert from the molecule counter from mole to atoms, molecules, and particles. Let's first look at the basics. We are surrounded by molecules. Most abundantly and famously known are carbon, oxygen, and nitrogens. But these molecules are so small in size, they are invisible to our eyes. For example, a drop of water molecule you can see is made out of many small individual water molecules. And that we consider the quantity of each of these molecules to be countable. So how do we count them? We count them by a number that we called in a unit of moles. This unit counter mole of a substance can be further converted into other units, such as particles of a substance, using the Avogadro's number, which is 6.022 times 10 to the 23rd. And it can also be equivalent to the atomic weight, which is the formula mass of the substance, in the unit of grams. Let's take aluminum as an example and look at what does 1 mole mean. So 1 mole equals to the atomic weight, which is 26.98 grams of aluminum. Okay, so on the periodic table, whenever you're looking at that particular weight, is the atomic weight per mole as the unit. Further, using Avogadro's number, we can convert the unit mole equals to the Avogadro's number, which is 6.022 times 10 to the power of 23rd aluminum of units of atoms, molecules, or particles. Remember not to confuse these units with the actual concept of a molecule or particle. Is the unit conversion of a mole of a particular substance equals to the Avogadro's number of atoms, molecules, or particles. Let's look at an example. In this question, we wanted to convert 0.1313 grams of nitrogen and 0.374 grams of oxygen into moles. Let's take a look at how we can do that. This type of a question, we always want to start with a given. And then we want to use the atomic weight that's given us from the periodic table to convert the grams into moles. So we first start writing down the given, which is 0.1313 grams of nitrogen, and divide by each mole of nitrogen, give us 14.01 grams of nitrogen. That's the atomic weight. Okay, and then once we cross off the grams of nitrogen in units, we have the units of mole. In this case, we have 0.009372 moles of nitrogen. Similarly, we can calculate the moles of oxygen. We start with the given of oxygen, which is 0.3749 grams of oxygen, and then we multiply by the divide by the atomic weight of oxygen by 1 mole of oxygen, give us 16.00 grams of oxygen. And then after crossing off the grams of weight at the top and the bottom of your equation, you have 0.02343 moles of oxygen. Once we calculate the mole numbers of nitrogen of oxygen, we can further use that information to convert the mole numbers into other units. For example, here, we wanted to convert it into atoms. To calculate the atom numbers of these elements, we need to first start with the mole numbers that we calculated in the previous slide. We are going to start with the 0.009372 moles of nitrogen and use Avogadro's number to convert the mole numbers into the atoms. And here, after crossing out the mole units, we have 5.644 times 10 to the 21st nitrogen atoms. Similarly, we can do that with the given previous slide's answers of the mole numbers of the oxygen. We once again multiply that by the Avogadro's number and give us the oxygen atoms number, which is 1.411 times 10 to the 22nd. So here I want you to be aware to know how to use your calculators. It gets really confusing if you don't know how to multiply it by the natural logs or the e's. Make sure you know how to use your calculators to multiply everything to the power of 20s and 23rd or the negatives of the powers correctly. Now we have successfully converting the unit grams into different type of units. We can do moles, atoms, and we can further use this information to actually determine the formula of this particular compound. So let's first look at what can we do. We can determine the formula of this compound with several ways, and then will all yield the same results. So the key idea is we wanted to find the ratio of the atoms. So we can use the comparisons of the ratio with the units of moles, atoms, or molecules. It will all give us the same results. So let's first look at the unit of mole. So over here, we have the unit of moles of oxygen divided by the moles of nitrogen, and it gave us the ratio of 5 moles of oxygen. Every 5 moles of oxygen, it would give us 2 moles of nitrogens. So every 2 moles of nitrogens, 5 moles of oxygens is needed. And that means our empirical formula of this particular molecule is N2O5. We can similarly do it with any other units since we had already determined the atom numbers from the previous slides. Here we can do it again, although with very different numbers. You can see the ratio stays the same. Note that with moles or atoms, you can also revert the order of oxygen of nitrogen. It doesn't really matter what you put on top or the bottom. Your ratio will be the same for nitrogen or oxygen. For example, here we have 5 moles of oxygen and 2 moles of nitrogen compared with 5 moles of oxygen on top, right? So this in decimal, it will look like something along the lines of 2.5. That means you need to remember that you have 5 moles of oxygen at the top. Okay, so if you revert that, this decimal number will look something along the lines of 0.4. That means you have a 4 over 10, which is the same as a 2 over 5 with the 2 moles of nitrogen on top. So it will give you the same ratio, which equivalent to the same empirical formula, 2 nitrogens and 5 oxygens, which is N2O5. After all the calculation we have just done, we had just came into a conclusion of the answer for the previous compound that we determined is N2O5. But is that the true compound composition? Could it be different? So what we just had is called the empirical formula. What is empirical formula? Empirical formula is the most basic ratio. So this is the lowest ratio of all the elements ratio. So in this case, it's 2 and 5, right? So every 2 nitrogens, we have 5 oxygens. But is that the molecular formula? What is the molecular formula? The molecular formula is the true actual composition of the molecule. So which means with our given ratio, our molecule actually could be something much larger in multiples. For example, it could be N2O5, or it could be something along the lines of, or it could be something along the lines of N6O15, and they could continue to multiply So is N2O5 our actual molecule? It can be, but it doesn't have to be. Then how do we determine that? If we wanted to know the actual molecule composition, we have to use the entire molecular weight. To determine if our molecular formula is actually our empirical formula, we have to know the actual weight of the entire molecular weight. So that means it's the full weight in grams of our structure. So in this case, we're wondering, let's just say our molecular formula is the same as the empirical formula. Then how do we find the molar mass of this compound? We had already determined our compound is N2O5. With that, we simply just multiply the number on the bottom, the subscripts, by the atomic weight of each element. So in this case, we have N2O5, and then we have 2 nitrogens plus the weight of 5 oxygens. So it's 2 multiplied by 14.01 plus 5 times by 16, and then you get 108.02 grams per mole. In this case, we have the molecular weight equal to our empirical weight. And of course, if the given says my molecular weight is 216, then you know that the actual molecular structure would have doubled all the ratios with your nitrogens and oxygens. That means you would have something along the lines of N4O10. So previously we have just learned how to determine mole numbers of a particular sample according to a given weight. Now let's try a different example. So in this example, we wanted to find the mass of the sample, which is in weight or grams of a particular sample with its given mole number. So in this case, we have dinitrogen pentoxide. So if you're wondering what that is, di is the prefix, which means 2. So we have 2 nitrogens with a penta means 5, which is 5 oxygens is what you have just calculated, right? So it's N2O5. If you are unfamiliar with the prefixes of these molecules, make sure you get familiarized with them. But in this case, we have 5.338 moles of N2O5. So how do we start this problem? We always start with the given. So starting with 5.338 moles of N2O5, how do we calculate the total mass of this size of the sample? Then what we do is we multiply it by the molecular mass that you have just calculated. So here that we going to multiply it by each mole of dinitrogen pentoxide have 108 grams of N2O5. And then you cross off the mole units. Now you ended up with 576.6 grams of N2O5. Let's try a different example. So in this example, similarly, it's asking that we have 5.338 moles of a sample, but instead of converting it to how many grams or in weight of this particular molecule that we have, we wanted to convert it to the units of molecules. That means we wanted to know how many molecules of dinitrogen pentoxide do we have when we're given with 5.338 moles of this particular molecule. So remember, do not confuse the unit of the molecule with the actual concept of the molecular structure of the molecule. Okay, so in this case, remember, whenever we wanted to convert from moles to molecule or moles to atoms, we wanted to simply multiply the mole number, which is what was given to us, by the Avogadro's number. So each mole of N2O5 gave us 6.022 times 10 to the 23rd molecules of N2O5. In this case, after you multiply the two numbers together and cross off the units in mole, you have 3.215 times 10 to the 24th molecules. Once we're giving the mole numbers of the entire molecules, we actually can also find the mole numbers of a particular composition of this molecule. For example, in this question, we're given the same 5.338 moles of the sample of dinitrogen pentoxide, but we wanted to know how many moles of just oxygen was given from this particular sample. Then what we do, we also start with our given, which is 5.338 moles of the sample. And then remember, inside this particular composition, with each mole of N2O5, there are 5 moles of oxygen was given to us. So therefore, we multiply it by each mole of N2O5, which goes on to the bottom, and that would give us 5 moles of oxygen. And once you cross off the mole, remember your moles, your units can only be crossed off from the bottom and the top at the same time, cannot do it with the top crossing off the top, and that you would be multiplying the unit, okay? So in this case, after you cross that off, you will have the mole number multiplied by 5. Therefore, it gives us about 26.69 moles of oxygen. Let's try one more example. In this example, a hydrocarbon gas is analyzed and found to be 81.71% carbon and 18.29% hydrogen by mass. Determine the empirical formula for this compound. So first, what we wanted to assume is everything in your composition has to add up to 100%. So no matter your composition has 2 elements, 3 elements, or even more than that, remember everything must be added to 100%. So in this case, we do have a 100% adding the carbon and hydrogen percentage together. What we wanted to do is we first automatically converting the percent sign to grams. But remember, you can never compare any elements by weight. What you can do, the counters of what you can do to compare the 2 elements is by their counters, which is their mole number. So what we first wanted to do, we want to convert everything into grams. So that means we have 100 grams of the sample. And the part of it, which is 81.71 grams of it, are carbon. Since we can't compare anything in grams, we have to convert this number into a mole number. And as we remember, in order for us to convert something from weight to mole number of a particular element or molecule, we need to divide the weight by the atomic weight of that particular element, right? So in this case, it's 12.01 grams. After you eliminate the units of grams, you have a mole number. So in this case, you have 6.803 moles of carbon. And then the rest of it, of course, is hydrogen. And this is the reason why you cannot compare by weight, because by weight, it looks like a carbon is such a big portion of this molecule. But remember, hydrogen has such small atomic mass, you're actually going to have way more moles of hydrogen than your carbon. So in this case, you're going to use 18.29 grams of hydrogen divided by the atomic weight of hydrogen, which is 1.008 grams. And this atomic weight is all given from a periodic table. You will have something along the lines of 18.14 moles of hydrogen. Once you have this particular mole number for each element, what you wanted to do is you need the ratio between the 2 numbers, between the 2 elements, okay, or between all the compositions. So if there is more than 2, you need to also find a common ground to divide the smallest mole number to make a 1, okay? So in this case, we're just going to use a bigger number to divide by a smaller number. No reason at all. You can do it totally the other way around. But again, whatever the ratio that you have, remember to keep it with the element that you keep either at the top or at the bottom, okay? So in this case, we're gonna put hydrogen on top and carbon on the bottom. So we will have 18.14 moles of hydrogen divided by 6.803 moles of a carbon. And you get roughly about 2.666 moles of hydrogens per 1 mole of carbon. So that is your ratio. But remember, whenever you wanted to write a molecular formula, you can't leave it as a H2.66. You can't do that. You have to put everything in the nearest integer. Here, whenever the rule of thumb is if you have 0.333, or if you see something along the lines of 0.67, you want to multiply that number by a integer of 3 to give a whole number. Okay, so in this case, once we do that, the top and the bottom, we're going to multiply by 3 over 3. You will have 8 to 3 in ratio, 8 moles of hydrogen to 3 moles of carbon. Therefore, it gives an empirical formula of C3H8. However, experimentally, that's not always the case. You don't know how accurate your ratio is. So sometimes if you get a ratio that's close enough to 2.5, you would just multiply everything by 2. So experimentally, this could be 5 moles of H with 2 moles of carbon. It will give you a molecular formula of C2H5. But in here, since we know it's accurate, it's given to us, we're going to go with C3H8. And remember, that is the empirical formula. In order for us to be able to find the actual molecular formula for this particular compound, you will also need to further know the molecular weight to begin with and divide that by the weight of your empirical formula. Then if it's the same, it came out the ratio to be 1, then you know your empirical formula and your molecular formula has the same structure. Otherwise, it could be in multiples, okay? But remember, it can only be in multiples of integers. So it can be in the multiples of a 1.5 or 1.3, then that's not correct. All right, so make sure either in your empirical formula or molecular formula, the subscripts of a particular element or subscript of that composition must be integer. That concludes our video. I hope you have learned a lot. So give a thumbs up or gives me a like to let me know it had helped you, and I will see you in the next video.